In this lesson, we're going to discuss the parallel axis theorem. So, as we've discussed, an object's moment of inertia depends on the distribution of its mass around an axis of rotation, which is why changing the axis of rotation on an object results in a different equation to determine its moment of inertia. So, you may have noticed this from our equation sheet. If we take the same rod, right, if we take any rod and put the axis of rotation through its center, it will have one equation. This moment of inertia will equal 1/12 times its mass times its length squared. But if we take that exact same rod and place the axis through one end, so it's rotating around its end now, rather than rotating around its center, then we end up with a different moment of inertia equation. That being that our moment of inertia equals 1/3 its mass times its length squared. So the new distribution of its mass around the axis of rotation results in a new relationship between its moment of inertia and the dimensions of its length or its radius or whatever that may be. So this brings us to an equation we can employ for this, which is that since an object will have different moment of inertia depending on where its axis of rotation is, we can use the parallel axis theorem to figure out where its moment of inertia, its current moment of inertia, or what we would call I prime, is in comparison to its moment of inertia about an axis intersecting its center of mass. So we can use this equation. This is the parallel axis theorem, which is that any given or any current moment of inertia, I prime, is equal to a moment of inertia around its center of mass plus its mass times its distance from that center of mass, the distance of the new axis from the center of mass. So let's put this into practice. And if we go back to our rod example, we can take a moment of inertia for a thin rod with a mass m and a length L as it rotates about an axis bisecting the middle of its length. And that is our example right here, where we have moment of inertia, where we have an axis of rotation bisecting the length of the rod, and if we are rotating it around that axis of rotation. And we know from our table of information, and again, in order to determine this, you'd have to integrate its radius relative to its mass. We know that our moment of inertia here for our moment of inertia around our center of mass, right? Because our center of mass will be directly in the center of that rod, is 1/12 times its mass times L its length squared, right? So we want to figure out what its new moment of inertia is, or I prime, if we take and we move that axis and shift it so that it ends up at the end of that rod. And now we are rotating that rod all the way around one end. So what is our new moment of inertia? So we take and we can use our parallel axis theorem here. And we could take for our new moment of inertia, or I prime, we can take our old moment of inertia, the moment of inertia around the center of mass, and we can add the mass of the rod, which is m, times the distance we moved that the axis of rotation, right? And so since we moved it from our initial location at the center of the rod to one end of the rod, how far we moved it is 1/2 the length of the rod. So our distance is 1/2 length equals the distance. So we can plug that in for D is 1/2 times L, and then we're gonna have to square that. Took and moved our equation over to the left-hand side of the screen just so we have some more room to work. And if we insert our moment of inertia equation for when the axis was at the center of mass, we have 1/12 times ml squared is our moment of inertia around the center of the mass, right? And we're going to add to that our m times 1/2 L squared. So that is m times, if we square the 1/2 L term, we end up with 1/4 times L squared, right? And then if we add these two, we get 1/12 ml squared plus, we need to put this into twelfths, right? So we can take 3/3 is 1. We can multiply that times our term over here, which is 1/4 ml squared. And from that, we get 1/12 ml squared plus 3/12 ml squared. And that gives us 1 plus 3 is 4, or 4/12 ml squared. And if we simplify that down, we end up with 1/3 ml squared is our new moment of inertia. So our I prime, after we account for the distance, so we moved our center, our axis of rotation from the center of mass over a distance of 1/2 L, we end up with a new moment of inertia that is displaced from our moment of inertia around the center of mass. And our new moment of inertia at the end, if we have an axis of rotation at the end of the rod, there is 1/3 ml squared. So if we take it, we compare that to our moment of inertia reference sheet, we see that our slender rod, if we rotate it around one end, we get back to that equation we expected, right? Which is our moment of inertia. If we rotate around an axis that is at one end of the rod, we get 1/3 m times the length of the rod squared, right? And again, that's different from our moment of inertia if we're rotating around the center of mass of that object, which would be 1/12 ml squared. So we can use this parallel axis theorem to determine if we take and we shift our axis of rotation from the center of mass of an object, what our new moment of inertia will be if we know the new location of our axis of rotation.